Virginia Tech before coming here, and I can, as someone who's recently moved here, and some of you are in that situation if you aren't from Salt Lake City, that both the academic environment and the living environment are just superb. The mountains get all the fame, but there's if there's anything you enjoy about outdoor activities, you can find it at world-class levels in Utah and around here. Hiking, climbing, going through canyons, water activities, and so forth. Water being white water and such. My interest is in vibration problems, and particularly in high-speed systems, whether that's spinning systems or translating systems. They tend to have especially unusual vibration behaviors. I'm not really going to discuss the phenomena too much. I don't have the time, but this is generally what I'm interested in, and I'll talk a bit about symmetric systems as well, because they also exhibit some unique vibratory behaviors that I find interesting to investigate. And I should say I am looking for new graduate students, good PhD students. So if you're interested in discussions about that, please send me an email. And it's helpful if you include basic information of a resume and possibly an unofficial transcript, things like that, so I can get a quick look at what your background is. But please feel free to contact me afterwards. So there's a lot of my activity relates to high-speed transmission systems, in particular aerospace gears, and they're now putting gears in aircraft engines. They haven't been there in the past. There are some terrific advantages of these things. I don't really have time to explain it, but for those of you who are familiar with aircraft engines, the gearbox is what connects the low-pressure turbine in the back of the engine, which spins at very high speed, to the fan blades at the front of the engine that spin at much lower speed, and we want to spin them at even lower speed if we could. But we can't when there's a rigid connection between the turbine and the fan blades, and a gearbox allows us much greater flexibility in choosing the optimal speed for the turbine and the fan blades. The problem is that these have to be, to make it work, they have to be really lightweight, and they cannot fail. If you have a gearbox and it fails, the engine is destroyed in a very catastrophic way. So that's where the dynamic challenge comes in, because the vibratory behavior is what generates the dynamic stresses that can cause the fatigue cracks that cause failure of the components. And so to mitigate this, we need a better understanding of how to model, analyze, and reduce the vibration phenomena that occur. You see on the right here some pictures of cross sections of gears. It may take a little while to figure out what those really are, but let's see. The teeth are mating right here at this connection, and the teeth are quite thick and beefy. But if you look everywhere else, how thin these gears really are, they aren't the gears that you're accustomed to seeing, and that's to make them lightweight. Otherwise, the calculations of the cost and benefit don't work out. So you can imagine that the vibration can be a big deal in these systems. This is what happens if you get it wrong. The failures are catastrophic. Parts, they break. You have these components that were spinning at thousands of RPM that are now flying around your aircraft engine. Some of them can go into the cabin of the airplane, but it's quite a dramatic failure. Very, very likely the airplane would come down. And there have been numerous examples of that in the helicopter industry. These examples are actually taken from helicopter applications. This is really just to show you a resonant behavior, that what happens when the vibration amplitude gets too big and resonance occurs is that the teeth actually lose contact. And you see that in the image on the left, where the colors the blue and the green will appear and then disappear at the various tooth contact locations. And that's because this is simulation showing high vibratory amplitudes where the teeth actually lose contact because of vibration. And that's really a devastating behavior, because the impact forces when they re-engage are extremely large. The animation on the right, if you look at it for a couple seconds, you'll see that every other tooth is coming into contact. In this case, the vibration amplitude, which you can't see, is large enough that, for instance, that tooth came into contact, and now you see the next pair of teeth on the right, they never come into contact, and then the next pair will. You see there some re-engagement. By the way, I want to emphasize, I'm going to show you images because they're of gear systems. I want to emphasize, if you join my lab, I don't train you to be an expert in gear systems. I am not. I don't know how to design gears. I'm not that interested in learning how to design gears. What I am interested is in dynamics and vibration. And I like modeling mechanical systems and using those models, whether they're mathematical or computational models, to predict the motion of these vibratory systems. I am interested in dynamics, and people that join my lab, the expertise that they get when they leave the lab is expertise in dynamic systems and modeling and prediction of motion. It's not in the details of gear systems. And that was what attracted me to the field when I was a graduate student. I knew I was interested in that. I'd liked freshman physics. I'd liked the sophomore dynamics class. I was fascinated by gyroscopes. This is what drew me to the field. Here's another animation of a couple mating gears. This is a PhD student in my lab that's developed a really unique computational tool that is now in use in the aerospace business. This is predicting some of the vibration modes of that system. And he developed the graphics of this. It's the reason he has this kind of hypnotic traveling wave behavior is because of the high speed motion of the system induces vibration in a way that wouldn't occur if the system were not spinning at high speeds. These are some of the tools that we use. By the way, there's some experiments that show you some gear noise. Yeah, good. I think the sound is gone. Those are some experiments built in my lab some time ago. You could hear the noise. Normally, of course, these gears would be encased in a housing, so you couldn't see them. But the tools are, what I really love is the modeling in the upper left, building some mathematical tools. I'm far from a mathematician, but I like working with mathematical models and building MATLAB simulations and testing them. Those are, in my opinion, the really valuable things that universities can produce. We use computation, which is the image in the upper right, a lot. I used to do pretty large-scale experiments. I'm not doing those at the moment, but we get some excellent experimental data from our industry partners, and we rely very heavily on that. Another area that I work is high-speed bearing dynamics. Again, I'm not that interested in bearings themselves. They seem kind of routine, but as a dynamic system, they're brilliant. They have nonlinear features. They have what's called time-varying features and parametric resonances, and some really, the vibratory behavior is fascinating. The application itself is somewhat mundane, but I'm much more interested in is the research interesting, not is the application sexy. But these things spin at quite high speeds as well, and that introduces some unique failure modes and vibratory phenomena. You see some of the damage that can occur in the image on the lower right. And the final thing I'll mention, which is an area that I really am looking for someone to help with. I've had former PhD student, current postdoc, who has done what I think is superb work on the vibration of general symmetric systems, and the images show some examples of these systems. But I'm not, in this case, I'm not interested in any of these particular examples. It's the vibration of systems that have symmetry, any type of symmetry. These are just examples. And this person in my lab, who's still on my team, did some brilliant work where he went over the mathematics, came back with this idea of group theory, which really is a wonderful tool to analyze these systems. But it's, in my opinion, wildly underappreciated and underexplored in engineering applications. And so he initiated an investigation application of that to symmetric systems and has come up with some research that I think is really superb. It's his work. And I'm looking for some people to get involved and to continue that activity.